Sound. Hey, everybody. So we're going to be looking at applications of exponential equations today. So application number 1 is called radioactive decay or half-life. No, not the video game. So when you have a radioactive isotope of an element, and it doesn't even have to be an element that's radioactive usually, for instance, carbon-14, of course, we're all made of carbon in large part. And carbon on its own, normal carbon, carbon-12, is not radioactive, but carbon-14 is. It's called a radioactive isotope, and over time it decays into nitrogen-14. And it has something called a half-life, which means that every half-life, half of the amount of carbon-14 is still left over and has not decayed. So carbon-14 is what this means right here, has a half-life of about 5,700 years. Sometimes you'll see that figure as 5,730. This means that every 5,700 years, half of the remaining carbon-14 has decayed into nitrogen-14 compared to the previous half-life. So half of whatever still remains will decay. So let's check out an example of that. So we have I don't know, a mammoth or something, some sort of organism. It does have to be organic. When it died, it had 32 units of carbon-14, maybe 32 nanograms or something. It's going to be pretty small. And I've represented the 32 units here with these 32 bright cyan circles. And I've got my graph here, half-lives since death. So 0 half-lives. This is when it died. It had 32 units of carbon-14. So 5,700 years later, which is 1 half-life, 16 units of carbon-14 remain. So that is exactly half. In fact, you can compare the height on the graph. After 1 half-life or 5,700 years, we now have 16 units of carbon-14 compared to the 32 we started with, and this is right at the halfway mark compared to the 32. So half of what was there had decayed. So 5,700 years after that, we have, behave yourself. So 5,700 years after that, so a total of 11,400 years, 2 half-lives later from death, 8 units of carbon-14 are still left. So again, you can see right here, half of what had been there, so half of our previous 16 units have decayed into nitrogen-14. So every 5,700 years, or every half-life, you have half the amount left over. So after another 5,700 years, we again have half of the previous remaining amount left over. So we started with 32. Half of that is 16. Half of that is 8. Half of that is 4. And 4 is where we currently are. So 4 units of carbon-14. So what do you think is going to happen after another 5,700 years? How many units of carbon-14 will be left? Answer that right now. So hopefully you said 2 units. 2 is half of 4. So again, we went from 32 to 16 to 8 to 4 and to 2 units. And finally, after 5 half-lives, we have 1 unit of carbon-14 left over. And of course, it would keep decaying from there until it gets too small for us to detect, really. But each time by half the amount. So there are 2 formulas you're going to need for half-life this year. The first formula we have, let's see if I can write on this screen. This is my first time doing this, you guys, kind of. So I've got right here, this is for half, obviously 0.5 is half, so that is for half-life. On both of these equations, A sub 0 or A naught is your initial amount. So initial amount, that's your starting amount of whatever the substance was. Okay, A is going to be your ending amount. So if you want to know how much is going to be left over, let's say after, I don't know, 100,000 years or so of your radioactive substance, your ending amount would tell you that after you put whatever time period you want in for T. So speaking of T, T stands for time. So T stands for time in years. So time in years. And now each formula has one other variable that is different. So H is for half-life. H is for half-life. So in our previous example, it was 5,700 years. Your half-life is 5,700 years. Depending on what your radioactive substance is, it could be a lot less or a lot more. And then finally, we see right here, let's use a strange color right here, why not? This, that's not red. Let's try that again. I'm gonna have to edit this out. So then we see this strange symbol right here. That is called the Greek letter lambda. Lambda. And lambda, I'm going to have to put it here. Lambda, kind of like that, is your decay constant. So if the formula asks you, rewind. Let's see here. Okay, so the Greek letter lambda in this case stands for your decay constant. So decay constant. So if you have a question that's asking for the decay constant of whatever your radioactive substance is, you need to use that second formula. And we're going to do an example of each one right now. Why is this so difficult? All right, so example number 1, an organic sample is estimated to have had 32 nanograms of carbon-14 in it when it died. It currently has 10 nanograms of carbon-14. Using a half-life of about 5,700 years, how long ago did this animal die? Why can't I make this smaller? That's irritating. All right, so we're going to take our formula, which you can currently see on your paper there, and we're going to take so we have our kind of current amount right here, 10 equals, and then we started with 32 nanograms, and then half for half-life, and then our exponent we have T, so T divided by H. So we're looking for T. We want to go how long ago this animal died. So T divided by 5,700. Okay, so now I need to use reverse PEMDAS until I can get that 1/2 to the power all by itself. So I'm going to divide by 32. Okay, so I get 0.3125 equals 0.5 to the power of T over 5,700. Okay, good so far. So we've done our multiply divide step. Now we're at our exponent step. So we're going to need to change our equation into logarithmic form. Now, because I decided I was going to be clever with this video and do it in a PowerPoint with this huge stylus writing pen deal, I have no more space. So make sure you have the top part written down because I'm about to erase it. Okay, make sure you got it written down. Okay. All right, so I've switched pen colors. And yeah, got it. Thanks. Let's make our pen a little bit smaller. Why don't we try that? Look, you guys, you're discovering this stuff along with me. Isn't that exciting? Okay, so I'm going to take my expression now, and I have a base of 0.5. So I'm going to put log and base 0.5 of 0.3125. And I know that's going to equal t over 5,700. Okay, so the left side I can put into my calculator. So this right here, I'm going to put in my calculator right here. So I get 1.67, wow, 1.67807 equals t over 5,700. Okay, and then I just need to multiply both sides by 5,700. Okay, so I get t equals 9,565.01 years. And you can confirm that in your calculator, that it has taken, so here's your 10 nanograms left, and it takes, not quite 2 half-lives. Remember, 2 half-lives was 11,400, so 9,500, that's right about in there. It's a pretty good estimate. Okay. All right, example 2. Carbon-14 has a half-life of approximately 5,700 years. What is its decay constant? So now we're going to be using our second formula. So I've got my ending amount. Well, let me write the formula first. So I've got A equals A sub 0 times E. Wow, really? Times E to the power of negative lambda times T. So I just want to know its decay constant when I know the half-life. So half-life means that half of the substance is left over. So honestly, I can put anything I want for A naught and A, as long as A is half of A naught. So I'm going to pick just 1 and 2, because that'd be simple to work with. Oh, you know what's simpler? Okay, I'm just going to put 0.5. It's a half-life, so there's half left over. And then my beginning amount would be 1. So 1 times E to the negative, oh my God, I hate this. So I'm going to put 0.5, because I'm looking for the decay constant when I know the half-life, equals 1 times E, and then to the negative lambda times T power. And you know what? I don't really need that 1 there, so let's just erase the 1, because 1 times a number is itself anyway. Okay, so I'm going to do reverse PEMDAS here. Is there anything to add or subtract or multiply or divide? There is not. I just have an exponent. So I'm ready for my exponent step. And just remember that when your base is e, like it is here, you have a special log button, so the natural log, so ln of 0.5 equals negative lambda, and then times t. Now for t, we're going to go ahead and put the half-life. So 5,700. Okay, so then type in natural log, so ln of 0.5 in your calculator. And you get negative 0.69. 3147. You know what? This is way too hard with the PowerPoint. Sound check. Yay. So take a look at the formulas that are in your foldable, and we're going to go ahead and label the parts of the formula. So we've got two formulas here, one that is used if you know, let's say the ending amount of the substance, the beginning amount, the time, and the half-life, and one where you're trying to find the decay constant. So let's first label, so T in this case equals time. The amount of substance left after all that time is going to be your A. A sub 0 is going to be your initial amount. Now both formulas each have one variable that is all their own. And in the first one we have the H. So H equals the length of the half-life. So in the example of our carbon-14 was give or take 5,700 years, give or take 30. And you will have to make sure that your half-life and your time are in the same unit. So if your time is in years, your half-life also needs to be converted to years if it's not already. And this other formula, we have, well, of course we have E, which is not a variable, but instead is approximately 2.718. So just be careful that you don't consider that one a variable. Now, this one right here is the mystery. This is the Greek letter lambda. The Greek letter lambda like that, and it's a negative lambda in this case. So lambda is called your decay constant. Which is something that physicists can use to kind of compare different radioactive substances and how long they take to decay. So we're going to try two examples, one with each formula, so you can see how they work. So go ahead and open up that foldable. All right. Example 1. An organic sample is estimated to have had 32 nanograms of carbon-14 in it when it died. It currently has 10 nanograms of carbon-14. Using a half-life of about 5,700 years, how long ago did the animal die? So we're going to use the first formula. So we're not asked for decay constant, so we don't need to worry about this one right here. We're just going to use this one. So I'm going to write my formula first. So now I need to figure out what part of the formula I know, what variables am I given, and then what do I need to find out. So I know that our sample, I don't know, mammoth skeleton or something, who knows, but it's got to be something that was once alive, is estimated to have had 32 nanograms of carbon-14 when it died. Now, here's a mistake that students make. Carbon-14, this is, the 14 is part of the name of this isotope of carbon. Okay, so normal carbon is carbon-12, and this isotope, which is radioactive, is carbon-14. 14 does not go anywhere in this equation. It's part of the name of this. So don't try to put 14 in there. We instead need to look at the amount. So 32 nanograms. So that's what we started with. So I'm going to put that here for A sub 0. And then it currently has 10 nanograms of carbon-14. So currently, right there for A. And then times 0.5. And then to the power of T over H. Now, T is the amount of time that it's been since the animal died. And I don't know that. That's what I'm trying to find out. So you're going to leave your T there. But I do know the half-life. It was given to me, at least an estimate of it. So approximately 5,700 years. And now to solve this, I'm going to be using reverse PEMDAS. So start with add or subtract first. Do you see anything that you can add or subtract? There is nothing. Then is there anything I can multiply or divide? So remember that 0.5 is the base of the exponent. So don't try to divide by 0.5. However, I am taking 32 times this whole power, so I can divide by 32. And I get 0.3125 equals 1/2 to the power of T over 5,700, which puts me at my exponent step. And an exponent step in this case is where I need to isolate my exponent. I need to get it out of there. I need to get it down. So I'm going to use a logarithm. I'm going to put this in logarithmic form. So I have log base 0.5 of 0.3125 equals T over 5,700. Okay, now remember, this left side is just a number. It's really complicated looking, but it is just a number. So there's no variables here anymore. The only variable that we have is left on the right side of the equation. So we're good. So I'm going to go ahead and put that in my calculator and get an estimate. Okay, so then our exponent step is done. And now we just have to do what used to be in parentheses, which was up here, or in the grouping symbol. And I'm just going to multiply by 5,700, which gives me 9,565.01 equals T. So this animal has been dead about 9,565 years ago. That was when it died. Poor animal. Okay, so as long as you can get it set up with all your values in the right spots, then it's just a matter of reverse PEMDAS, and then you get your solution. So let's look at number 2. We're again working with carbon-14, which we're still using a half-life of about 5,700 years. Now I want the decay constant. So I'm going to look at that second formula, this one. And I'm going to start by writing it down. I'm going to switch pen colors just because I can, why not? All right, so I got my formula written down. In fact, I'm going to zoom in a little bit. So carbon-14 has a half-life of approximately 5,700 years. So notice they don't give us an ending amount. They don't give us a starting amount. But all we really need to know is that it has been one half-life. So I know that half of it is left. So I can use any numbers I want. Like I could say I started with 1 gram and I'm going to end up with half a gram, or I started with 4, I'm going to end up with 2, whatever you want, as long as it's half of it, because it is a half-life. I'm just going to take the easy way out and say I end up with half. I started with 1, and then times e to the negative lambda times t, which is the number of years in this case that it has been. So after 5,700 years, half of it is left. And then I don't really need a 1 here, so I'm going to simplify this a little bit. So 0.5 equals, I don't need to write 1 times a number. And then I'm just going to rearrange this so it looks a little better. So negative 5,700 times lambda, just so I have my variable at the back. Okay, so now I'm going to use reverse PEMDAS to solve it. So do I have anything here to add or subtract? No, nothing at all. Do I have anything to multiply or divide? The only thing I have to multiply or divide is in the exponent, which is in the parentheses step. I can't access that yet because it's up there. It's blocked from me right now, so I can't do that. So now I'm at the exponent step and I get to finally free my variable so that I can get to it. So remember now, when you turn this into log form, you could write log base e of 0.5 equals negative 5,700 lambda. Or, remember there's a shortcut for this, so I'm actually going to do this in a different color. Remember log base e is the same as natural log ln. So I would recommend, instead of doing log base e, I would recommend doing ln of 0.5 equals negative 5,700 lambda. And I would recommend not doing that way. That's just extra button presses in your calculator, and nobody likes pressing buttons. So I'm going to go ahead and get an estimate for this. So natural log of 0.5, which is negative 0.693147 equals negative 5,700 lambda. And then, so I've done this. Now I'm just in my parentheses step, so I just need to divide by negative 5,700, and I'm done. So my decay constant is this puppy right here. All right, I would recommend taking a short break because this is kind of a long video before we go to compound interest. So pause the video, go stretch, and then come back. Okay, welcome back. Actually, not welcome back yet. I'm gonna fold this so it's out of my way. All right, welcome back. So now we're going to look at our second application, which is compound interest. So when you invest money or borrow it, like say on a credit card, your money is going to earn interest, whether that's interest earned for you or interest earned for your bank. And for most investment and credit accounts, it's something called compound interest, which means interest builds upon interest. So it's not just your original amount that's earning money, it's all the interest that you've earned also earns its own interest. So it's a faster way of building wealth if you're the one investing, and it's a faster way to owe people more and more money if we're talking about a credit card. So it could be really good for you or it could be really bad for you, depending how you manage that money. So let's look at these two formulas that we have here. You'll notice one of them has our good friend E in it, and the other one doesn't. So A is going to be our ending balance. And then P, so P stands for principal, but it is your initial amount. So P stands for principal, but that's your initial amount. And then you'll notice that both formulas also have an R in them. So R is for interest rate. So R is for interest rate. And the last thing they both have in common is T for time, and it's almost always going to be years. So T equals time in years. Okay, now you'll also notice that each formula has one thing in it that's different than the other. So this one, of course, has E, which is our old friend. That should be approximately equal to, so approximately 2.718. This other formula, however, uses the variable n. And this n stands for the compounding periods per year. And we'll kind of talk about that. Now note that n is twice in this formula, so you're going to have to use it both times, not just one time. And compounding means it's how often interest is calculated per year, basically. So if it's compounded quarterly, then every 3 months, then more interest is calculated on the account. Or if it's daily, then every day more interest is compounded or calculated onto the account. And the more often, the better it is if you're the one who's getting the money. Whereas if it's less often, then that's a little less good for the person getting the money. So we're going to look at a couple of examples of this as well. And the best possible scenario is continuous compounding. So that means new interest is constantly being calculated and added to the account. It's constantly building on itself. I don't personally know of any actual bank that does that, but hey, I could be wrong. Maybe there's one out there that does. Most banks do monthly or daily. Like the big banks, Chase, Bank of America, they tend to do monthly and daily. So it just depends on your bank. But let's look at example 1. So example 1, Jonathan puts $5,000 into a CD, so that means certificate of deposit. It's a type of investment, which earns 0.85% interest annually. His interest is compounded daily, so that means every day his bank or whoever he has the account with will figure out how much interest he earned that day and add it onto the account. How long will it take his account balance to reach $5,100? So since we're compounding daily, we're not compounding continuously, so we're going to be using this first formula. You only use this one if it says continuous compounding. So we're going to be using this first one. So go ahead and write it down first. All right, so now we have to look through the problem and see what variables we have a value for and which ones we don't. So we know Jonathan puts $5,000 into the account, so that's his P, that's his initial amount. That's what he starts with. And we know he earns 0.85% interest annually. I don't know why I can't say that number today. Now, this does need to be written as a decimal, not as a percent. So that means we need to take our percent and either divide it by 100 or move that decimal point twice. So your R is going to be 0.0085. So be really careful that you don't put the number just the way it is. You have to convert it into decimal format. And his interest is compounded daily, so compounding periods per year is your n value. So you have to think how many days per year. Most years it's 365, so n equals 365. And finally, we want to know how long it will take. So how long will it take? So that's going to be our T for his account balance to reach $5,100, and that is your ending balance. So we know we're going to be looking for T, which is in the exponent, and we have everything else. So let's go ahead and plug these numbers into our formula. All right, so there's my formula. Now, just like the last one, I am going to do a reverse PEMDAS to solve this. So you're going to start by adding or subtracting anything that's not in parentheses. And unfortunately, the only thing that we have is in here, which in just a second, we're actually going to simplify this. You know what? Let's simplify that now, because that's really messy looking. Notice that in the parentheses, there are no variables whatsoever. So just put just the part in parentheses, put that in your calculator and get a number for it. It's going to be so much easier. So this right here is going to come out to 1.00002. And then go ahead and write out the rest of it. Okay, so that's a lot better looking. So now the base of my exponent is 1.00002. And I still have nothing to add or subtract, so I'm going to try to multiply or divide, and I sure can divide by 5,000. No room. I divide by 5,000 on both sides, which gives me 1.02 equals 1.00002 to the power of 365t. And my multiply divide step is done. So now I'm ready for the exponent step. So I need to get this t out of the exponent. I need it to be down at this level where I can work with it. So I'm going to convert this to logarithmic form. And as usual, this right here, as messy as it looks, is just a number. So go ahead and put that in a calculator and get an estimate for it. And finally, the last thing we'll have to do is divide by 365. So let me come back up here so I have some space. And I get that t is approximately 2.713 years. So about 2 years and between 8 and 9 months for his interest to amount to the point that his account balance is about $5,100. Finally, our last example. Jonathan puts $5,000 into a CD for 5 years. So, he's doing the same thing. Now he got super lucky. His interest is compounded continuously. So what interest rate would he need if he wanted his balance to reach $6,000 after 5 years? So he wants to earn $1,000 in 5 years just by having his money in an account. Can't we all be so lucky? So since I'm compounding continuously, I need to use my second formula. And we call this the PERT formula, like the shampoo PERT. So the PERT formula. All right, and again, we have to figure out what we know from this problem. So he puts $5,000 into the account. That's your p-value. It's your starting amount. For 5 years, so there's t. And he's compounding continuously. That's what the E is for. Then it says what interest rate? So we know we're going to find R. We don't know what R is. And he wants his balance to be $6,000. So that's your A value. So now I'm going to go ahead and plug these values into my formula. And then I want to use reverse PEMDAS to solve. Okay, so first, can I add or subtract anything? No, there's no addition or subtraction in sight of this problem. There is some multiplication or division though, and we're having 5,000 times this power, so I can divide. And I did go ahead and write r times 5 as 5r. All right, so we're at the exponent step now, which means I get to put this in log form. And remember, when your base is e, you have two ways to do that. You could say log base e of 1.2 equals 5r. Or you could do, remember log base e is the same as ln. So you could do ln of 1.2 equals 5r. And I highly recommend you using this one if your base is e. It's a lot fewer button presses in that calculator. And then this is just a number, so go ahead and put that in the calculator and get an estimate for it. And finally, just divide by 5. And since we are talking about an interest rate, we want to convert this back to decimal or percent form. So either move that decimal twice to the right or multiply by 100, and you get approximately 3.65% interest. So good luck finding that, Jonathan. How long was that? Goodness gracious.